Okay, this person, Rocio Harvey, say his name, strikes a .058 kilogram ball with a force of 272 newtons and gives it a velocity of 62 meters per second. How long was Rocio's club in contact with the ball? We have a formula that for impulse, which is force times the change in time that we have a collision for, is equal to the change in momentum that happens. So we were given the change in momentum, and we were given the force. So the force is 272. We can solve for the change in time. Change in momentum is momentum final minus momentum initial, which is mass times final velocity minus mass times initial velocity. And the final velocity is 62 meters per second. So we're going to plug in 62 right here. And the mass is 0.058. So if we plug those values in, the final velocity, or I'm sorry, the initial velocity is 0 too, so this whole term drops out. So all we have is 272 times change in time equals 0.058 times 62, and we're solving for change in time, which is 0.013 seconds is the length of time the club is in contact with the ball. All right, next question then. A hockey puck has a mass of 0.115 kilograms and it's at rest. A hockey player makes a shot exerting a constant force of 30 newtons on the puck for a time of 0.16 seconds. With that speed, or with what speed does it go towards the goal? Well, once again, force times change in time equals change in momentum. So we have 30 newtons times 0.16 seconds equals final minus initial momentum. Initially, the puck's at rest, so that's 0. So we have final momentum on this side of the equation, which is just mass times final velocity, which in this case is 0.115, and we can find out the final velocity. Okay, if you solve this final velocity, 41.74, and that'd be meters per second. Okay, next question says a 0.150 kilogram ball moving in a positive direction at 12 meters per second is acted on by an impulse shown in the graph. What is the ball's speed at 4 seconds? Okay, why know the ball's speed at 4 seconds? We need to look at the units on this graph. So we know that impulse is equal to the change in momentum. So we know that if we were to take force and multiply it by time, we know that would be the area on this graph, and that would give us the change in momentum. So if we want to know the speed at 4 seconds of this ball, we need to find the change in momentum. And to do that, we're going to find the area in this curve, which is the area of the triangle, which is 1/2 base times height. So it's 1/2, the base is 2, the height is 2, so it's just 2. And that's momentum. So momentum is mass times velocity. So this is mass times final velocity minus mass times initial velocity equals 2. And we know the mass is 0.15. The final velocity is what we're looking for. And we have the initial velocity is 12 meters per second. So we're solving this equation right here for final velocity. So add these terms over and divide by 0.15, in which case you get, so final velocity would be 25.3 meters per second. Next question then says an animal rescue plane is flying due east at 36 meters per second, and it drops a bale of hay from an altitude of 60 meters, as shown. If the bale of hay weighs 175 newtons, what's the momentum of the bale the moment before it strikes the ground? We want the magnitude and direction. So let's set up the x and the y information again, like we did in Unit 1. In the x, we have a speed of 36 meters per second. That's going to stay consistent. I don't care about the distance and the time for that direction. Let's move to the y direction. In the y, we have an initial y velocity of 0 meters per second. The final velocity in the y is what we're looking for. The acceleration is negative 9.8 meters per second squared. The initial distance is 60, and the final distance would be 0. So we can find out the final velocity in the y then. The equation that we can use, final velocity in the y squared equals initial velocity in the y squared plus 2 average acceleration times change in distance. Final velocity is what we're looking for. The initial velocity is 0. Negative 9.8 goes in for acceleration, and the distance is 60 here. It's actually negative 60 here if you do final minus initial, which is good because we don't want to take the square root of a negative number. So that gives us final velocity of, if we solve this, take the square root of both sides, 34.3 meters per second. That's our final velocity right here. Okay, now what I'm going to do is look at the object. Obviously it fell like this, and we're at this point right here. I'm going to draw a free body diagram on it. On the free body diagram, I have a velocity pulling downwards of 34.3 meters per second. And I have a velocity going this way of 36 meters per second. Let's find the overall velocity, placing these vectors tail to tip, and find the resultant, the overall velocity. And if we do the Pythagorean theorem, that gives us 49.7 meters per second. Now that's what we want for momentum. It asks us for final momentum, which is just mass times velocity. So all we have to do is multiply the mass times this velocity of 49.7. It told us that this thing weighs 175 newtons. So we can find the mass if we just divide by 9.8. And that gives us 17.86 for the mass. If we multiply that by the velocity, that gives us a momentum of 887.8 kilogram meters per second. Okay, this problem also wanted the direction. So to give the direction, I have to give this angle right here, and I'll call it below horizontal. So to find that, I'll do inverse tangent. So inverse tangent of 34.3 divided by 36. And that gives me about 43.6 degrees below horizontal. So I would say below horizontal here. Okay, the next problem gives us a cue ball rolling with mass 0.16. Afterwards, the cue ball goes this way and the 8 ball goes this way after collision. And these are 45-degree angles. And it wants to know the velocity of each of the balls after collision. So this is a tough problem, but we can draw some vectors here. So here I'm going to draw this vector to represent the initial momentum of the cue ball. I'm going to draw another vector here. And it doesn't matter where we place vectors, so I'm going to replace these vectors all so that they're tail to tip. So I'm going to place the vector of the final velocity of, so this would be the momentum final of the cue ball. And then I'll replace the final momentum of the 8 ball here to represent that vector. Now, I know that this would be a 45-degree angle there. And if this goes down at a 45-degree angle, then this is a 45-degree angle here, which also makes this a 45-degree angle. So this must be a 90-degree angle then. So we got a triangle here. Let me draw it a little better for you. All right, so there's my special right triangle. Now, I know that because of conservation of momentum, these two momentum vectors have to add to be this one. So I can set up the special right triangle, I can set up the mathematical relationships I know for it. Like, for example, if this side is x and this side's x, it's an isosceles right triangle, this side would be x squared 2. Well, we know this side is mass times velocity for the cue ball originally, which is 4 times 0.16, which gives you 0.64. So set that equal to x squared root of 2, because that's what this side is. Divide by the square root of 2. And that gives you the momentum. I'm sorry. That gives you x. So this is 0.45 about. Now if that's momentum, I can set that equal to mass times velocity final for the 8 ball. And just divide by the mass, which is 0.16 again. If you divide by 0.16, that gives you 2.8 about for the velocity final, meters per second. And we know that it's going to be the same for this one because it has the same mass, and we know that these are both x, they're both isosceles. So the final velocity of the 8 ball and the final velocity of the cue ball are both 2.8 meters per second. Next problem then gives us a van running in the back of a compact car. So we have momentum initial has to equal momentum final. So initially we have mass times velocity for the van. no momentum from the car. Afterwards, we've got the mass of the van plus the mass of the car as they move off together, so times the speed of the car. Assuming that the friction on the road is negligible, calculate the speed of the van. I'm sorry, the van right here. So we're solving for that variable. So that'd be 2,575 times the velocity of the van equals 2,575 plus 825 times the velocity of the car velocity of both as they move off together, which is 8.5 meters per second. So we're just dividing by 2,575, and that gives us the velocity of the van, which is velocity of the van then 11.22 meters per second. Okay, next problem we've got momentum before is equal to momentum after. So momentum before, we have mass times velocity of one ball plus mass times velocity of the second ball. And then afterwards we've got mass velocity final for ball 1 plus mass of ball 2 times velocity final for ball 2. So originally we have 0.2 times moves with velocity of 0.3, and then the second one would be 0.1 times velocity of 0.1 equals, after collision both balls continue to move in the same direction, the speed of the 0.1 kilogram ball, which is our second ball, is 0.26, so we have 0.1 times 0.26 here. And then this 0.2 kilogram ball, we don't know the speed for that. We call that our first ball, so we're solving for that variable. So we're just going to multiply these numbers and add them to the other side, or subtract from the other side and divide by 0.2, and that gives you a final velocity of 0.22 meters per second. That's the speed of the first ball afterwards.